First of all, welcome everyone back to our Saturday Physics for Everyone program, and for braving with, dealing with all the windy weather out there. So my name is Jan Schemla. I'm filling in for Irene Lira Ansager, who is the program director for Saturday Physics for Everyone. Irene had to be at a conference this week and asked me to fill in. It's great for us to be back in person. This is the first semester back since the pandemic, where we can have these events in person. And we're really lucky to have a bunch of great talks lined up. This is our second to last talk for the semester. We'll have one in about 2 weeks. So the format for the talks, if you've been here before, our speaker will talk for about 45 minutes or so, and we'll have plenty of time for questions at the end for about 15 minutes. And Professor Gruebele has told me that it's fine if you want to ask questions in the middle of the talk. He'll gladly answer questions, but we'll also have time at the end for a question and answer session. Without further ado, let me introduce today's speaker. We're very lucky to have Professor Martin Gruebele here. Professor Gruebele received his Bachelor of Sciences and PhD from University of California, Berkeley, and then did his postdoc at Caltech, and then joined the University of Illinois in 1992. He's been a professor here since then, both in the Department of Chemistry and in the Department of Physics. Martin works on all sorts of different areas. My lab actually collaborates with him. He works on things at the molecular level, trying to understand how proteins collapse and fold into particular shapes, all the way to how animals behave. And I think that's reflected in the title of his talk, which is The Future Prospects of Science. So Martin has lots of interests, and you're going to hear about them today. Martin is the recipient of many prizes. He's a member of the National Academy of Sciences, a member of the American Academy of Arts and Sciences. He's also a fellow of the American Chemical Society, Biophysical Society, and Physical Society, and many more accomplishments. So without further ado, let me invite Martin to come up here and to start his lecture. Do you need to get hooked up on the microphone here? And Martin, I will ask that if people in the audience ask a question, that you repeat the question for everyone so it's recorded. Thank you.
And just for the camera, it's good. All right, we've got, you never know. I pushed the wrong button or something like that.
Let's show a big hand of applause to Martin.
Hey, everybody. All right, so first of all, I have to thank the physics department and students who run this for inviting me. What that means is that they think I can talk for 45 minutes without using too much jargon. Well, we'll see if that's true or not, but I hope so. That's the whole idea of this lecture series. And as Jan said, I'm more than happy if you want to interrupt with questions. The talk has 8 slides. I think my record low is I made it through 2 slides, and then the questions kind of went on. And I think I've made it through 7 at the max or something like that. So we'll see where we end up today. This is, of course, a big title, The Future Prospects of Science. And I don't think in 45 minutes I can cover all the future prospects of science, but what this talk sort of contains is some musings of mine of maybe some fields in physics that people are thinking about, where things might happen that don't make the New York Times all the time, so we don't hear about them as much. But also some of the problems that I think might beset science. Not that I have any solutions necessarily for them. It would be nice. But there's like things for us to think about as we move on how we actually run science and what we do at universities and so forth. So there's a little bit of that mixed in as well. I love this photo there of Europe. You can see the northern Italians and in the Netherlands, they're not very efficient about their use of lighting. The astronomers hate that because it lights up the night sky and it makes it harder to see things with telescopes. But it's a very artistic picture, and actually I will connect a little bit between art and science in the middle of the talk, because there's a lot of art in science, and there's actually a lot of science in art. For example, people, you don't learn science out of a book, right? If you want to do physics or you want to do chemistry or any of these sorts of things, you actually need to apprentice with somebody, right? That's why we have research advisors and students. And this is really the only way you learn it. I mean, it's like playing the piano, right? You don't sit down with a book and then read the book, and then you can play the piano. And you actually really need a piano teacher. And so there's the art in that. And likewise, in people, artists, whether they're visual artists or musicians or and so forth, there's a lot of technology involved in that, like pigments and how they work, and subtractive color, for instance, if you're talking about painting, or Fourier analysis of sounds, right, if you're talking about sounds. And there are actually a lot of artists, and this town has a lot of a music scene actually in it, that actually worry about this stuff. I know musicians that know Fourier transforms as well as I do, and because they actually need it, because they deal with electronic instruments and computational issues in music. So what I guess artists and scientists have in common is that we like to sort of deal with the unexpected. I mean, I know when we teach our classes, we usually teach material that's 30 years old, and we talk about stuff that we think we understand pretty well, although even there's actually often surprises. But the reason we really do science is because we want to do something where we'll be like, whoa, I didn't think this was happening. And artists do the same when they create works of art. So I brought a little demo here that is one of those things that was definitely unexpected for me when I first saw it. How many high school students are actually here? Because it's open to high schools. And raise your hand if you are one. Okay, there's one. All right. A couple, 3. All right, great. But to everybody else as well, right? We are all lifelong students, basically. So I actually did see this for the first time, but in a graduate class, not as a high school student. And in Europe, where you can probably tell I'm originally from, we call this a Druid stone. And in the US, they're a little more low-key, and they call it a rattleback, but it's the same idea. And if I take this little, wedge and I spin it, it actually all of a sudden turns around in the opposite direction. Okay, I'll do it one more time here. So I'm just going to spin it, and you would normally expect an object like this to just continue, going, as opposed to it stops and then turns around. And I use this in my graduate class to discuss something called vibrational angular momentum, or whatever that is. But the bottom line is, if you look at this pretty carefully, you can actually tell that as it stops spinning, it seems to sort of start vibrating, and then actually it spins in the opposite direction. And it turns out this thing does not violate the laws of physics. Angular momentum is being conserved. But what is happening is you're converting some of the angular momentum with the help of friction that holds this thing down to the table in such a way that there's actually vibrational angular momentum that goes in the opposite direction of the way it turns at the end, that's higher than the rotational angular momentum. And so the net spinning amount of energy that goes into spinning is actually the same, but it reverts direction. And this is one of those things, I saw that as a grad student, and said, wow, I had no idea this could exist, but I guess it does. And of course, the mechanics of this is pretty well understood, so you can read research articles where people describe how this thing actually works. Although, surprisingly, the really complete way of having figured this out is not that old. It's like maybe 15, 20 years, because mechanics is an old science, right? Newton could have, in principle, maybe figured out how this thing works, but the details of it took quite a while. So let me get to my first slide, and as I said, feel free to interrupt with questions at any time. And so I want to talk a little bit about this thing, neg entropy, and since this is jargon, let me explain what I mean by that. So, people often talk about how we have to conserve energy and be careful for the environment and all of that, and that's true. But it irks me every time that I hear somebody say we need to conserve energy, because energy, or mass energy anyway, is conserved. What we really mean by that is that we want to conserve useful forms of energy, and that means we want to create as little disorder as possible while we use energy. And that's what entropy is all about. Entropy is a measure of disorder, and we want to basically make as little of that while we do things. And so, for instance, if we burn gasoline efficiently in a vehicle, then we are creating less disorder than if we're burning gasoline inefficiently in a vehicle, and we conserve resources. To give you an idea of this, so there's a picture there of the sun, and the sun is yellow, and if you turn it into a temperature, that corresponds to a temperature of about 6,000 degrees Kelvin, so it's pretty hot at the surface. And these photons travel, the photons travel all the way from the surface of the sun to the Earth. Some of them might get scattered in the space in between, but a lot of them make it. And when they hit the surface of the Earth, they actually break up into a large number of photons and vibrations. Some get reflected back up, some go down into the soil, but you're turning them into photons that have a much lower energy or much lower temperature, namely about 310 degrees Kelvin, or as we might say, 60 degrees Fahrenheit or something like that, right? And basically something around room temperature. And this is an example of an entropy-driven process where we're starting out with this single photon and we're breaking it up into a number of photons that are actually no longer useful for doing work. And the reason is our environment is already at 60 degrees Fahrenheit, and having more photons at 60 degrees Fahrenheit just contributes to the temperature around us. It doesn't allow us to do work with it. So let me actually give you another example, a fuel example on the right-hand side, which illustrates how important it can actually be to work both sides of the equation. So nowadays, of course, there's a lot of news about how wonderful it is to have alternative energy sources like solar power and wind power and things of that sort, tidal power, maybe geothermal power and so forth. And that's all true. But actually, the single person in the world who has probably done the most to reduce our carbon footprint and is responsible for almost all the reductions in the last 10 years is not somebody who has worked on solar energy or any of these sorts of things. It's Dr. Hye-Kyung Timken. She's actually an alumna of UIUC, so we can be proud of her. And she works for Chevron, that is a gasoline energy company. And well, how did she do this? So if you look at these two arrows, on the left-hand side, the blue one basically shows you how much entropy is being generated. So that's the bad stuff, to basically have a car drive. And there's oil wells that produce entropy or disorder. There's refineries. There's the car itself, of course, that's responsible for a large amount when it burns the valuable fuel and turns it into water and CO2 that gets spewed out into the atmosphere. And then on the right-hand side, you see something that in principle you might think is completely zero-sum because you're taking a fuel like ethanol that's made from plants. And when that's burned, it does go as CO2 back into the atmosphere, but it came from plants and the CO2 will be reabsorbed back by the next harvest. And so, that's kind of a zero cycle. But actually, in fact, when you look at it, the agriculture requires energy, and not all of that comes out of the ethanol. It comes out of non-renewable power resources. The biorefining costs a lot. You have these reactors that are filled with bacteria that actually grow these fuels and refine them. And then the vehicle is good in this case, right? So that's why we as consumers feel great because, hey, we're a 1 versus a 74, right? But if you add all of it up, basically the entropy cost of creating corn ethanol, if you drove purely on that, is about 80% of that of gasoline. So you're saving 20%, which is good, I'll take that. But you're certainly not saving anything like 100%. So where Hye-Kyung comes in is that she actually developed a process tackling kind of the opposite end of the problem that actually greatly improved the way gasoline is refined and reduced the carbon footprint of that by an enormous amount, by really 10% or something like that. And this made, and it's one of those things, we know that in the far future, eventually we're going to wind down the gasoline economy and we're going to wind up alternative fuel sources. But for right now, that was something that happened much faster in a period of 10 or 20 years. And she did this by using what are called catalysts, which are basically things that make chemical reactions run better. And she came up with these exotic catalysts that are called ionic liquids that are like a salt, like your table salt, right? And most salts are just like white or maybe colored grains, right? They're solids. But it turns out these salts are actually liquids. And this allows them, but without any water or anything in them. They're just like only the salt ions, but they turn out to be actually liquid at room temperature. And this allows them to be used very efficiently to catalyze these processes with producing a lot less entropy. You don't need things like nasty acids like concentrated sulfuric acid or hydrofluoric acid or stuff like that. That's actually normally used in these refining processes. And so while, certainly, wind power and all those things sort of helped reduce the carbon footprint, this took the petroleum industry and really lowered its carbon footprint. And it's basically the invention of a single person that made a difference because she decided to get into that field. All right. So, since I used the word future prospects, right, I should talk a little bit. If there's, go ahead. Yeah, absolutely.
Is anyone working on reducing the cost?
Yes, so there's also a lot of people who are, of course, interested in that. In fact, there's lots of experts that we have on campus right here at the University of Illinois that are working on that. And basically what it boils down to is a lot of that cost comes from large agricultural machinery, a lot of it, I'm afraid, does not run on ethanol, but runs on other kinds of fuels like diesel fuels and things of that sort, and actually coming up with alternatives for doing that. It's difficult because, you know, crops are a seasonal thing that has to be timed right. You can't just sort of do things whenever you want. You have to time it with, you know, what's going on with the plants. But it's definitely something that people are thinking about. Yeah, absolutely.
What's an example of one of the catalysts that Dr. came up with that helped the process?
Yeah, so basically what these catalysts are, they consist of imidazolium ions, which are little circles of carbon. So you take like a small number of carbon atoms, and they have a nitrogen in them, and they're negatively charged, so that's the negative ion. And then they might have something like lithium as the positive ion. Lithium is a big favorite these days in a lot of ways, right? We love lithium batteries as well. And because they're catalysts, you don't actually need huge quantities of them, because, you know, otherwise it wouldn't be that great to have these really weird, complicated organic compounds and need massive amounts, but you actually need very small amounts of them to run these processes. And so that's why, you know, that helps.
Could I ask one also?
Yeah, absolutely.
Yeah, I wonder if you could, you know, explain why we consider entropy to be a very important measure of the badness of, you know, as opposed to, for instance, you know, greenhouse gas emission.
Right. Yeah, so greenhouse gas emission is actually just a source of entropy. So let me give you an example. One of the greenhouse gases, CO2, right? If that's in the atmosphere, let's do the case without and with. So, and I'm going to oversimplify because I'm picking one molecule out of a lot of things that are very complicated. So when you take these photons that have been generated at 300 Kelvin, so they're basically just thermal heat, right? Some of them get absorbed and they help maintain the Earth at the temperature we want, like around 300 Kelvin. And some of them get reflected back into space. Okay? In fact, about half of them get reflected back up. Right? And if you have nitrogen or oxygen in the atmosphere, it turns out those molecules actually do not absorb these 300 Kelvin photons, so that heat radiation, and so that radiation is able to go back out into space. Okay? Carbon dioxide happens to have a vibrational frequency that actually can be exactly absorbed by those, can absorb those heat photons. And so what happens is a photon that would have gone with 100% probability back into outer space, when it hits one of these molecules, it gets absorbed. The molecule will then randomly tumble around and will re-emit the photon, losing the memory. That's the entropy, right? The disorder is increasing of how it was oriented. And when the photon is re-emitted, it could actually be emitted backwards or 50-50 downwards. So what you're doing is you're putting this molecule in there, and something that would have 100% gone into outer space now has a 50% chance of going right back down to the Earth again, which contributes to the heating. So, does that help?
I'm wondering why the direct relationship with entropy.
Yeah, so the direct relationship with entropy here is that a photon that was in a specific state going upwards is absorbed and is completely randomly re-emitted. So again, you've increased the disorder of the system by, before you knew it was going up, afterwards you have no idea which direction it's going. That's an example of increase in entropy. Does that make sense?
Yeah, I'm sure there's no single measure of, you know,
yeah, this is, yeah, you know, there's lots of things. This is just one example exactly of what contributes. Any other questions? Okay. So let's go to a couple of examples. These are completely random. I could pick 100 completely different ones, right? And I think they would be quite interesting as well. So how many people here actually read things like either online, or maybe you even have the old-fashioned paper version like I do, like Scientific American or something like that? Like I'm definitely one of the subscribers. And, but as I think you all know, when you read a magazine like Scientific American, it seems to be heavily geared towards dinosaurs, you know, wormholes, you know, weird quantum cryptography effects or whatever. That's what people like to talk about. So there are certain kinds of things in physics that do make the press, and in paleontology or other branches of science pretty regularly. But there's also things that are maybe a little bit more quiet and don't necessarily generate as much press, but are still, I think, very interesting. It's not that they don't get any press. You can find something on it, you know, if you sort of look around a little bit, but it's not quite as much in the foreground as some of these other things. I guess I have alien life here as another thing. I actually am a firm believer, and I use the word believer because I don't know for sure, right? It's a question of, do I think so or not? That our ability to use space telescopes in the next 20 years, with the Webb one being one of the, you know, the next generation, is actually going to get good enough that will be able to map out planetary atmospheres around exoplanets that are 10 to 100 light years away, and actually tell if the atmospheres of these planets contain combinations of gases that are far out of equilibrium. Like on the Earth, for instance, in its atmosphere, you can measure both some methane or natural gas, which is easily oxidized by oxygen, but there's also a lot of oxygen. It's very unlikely that some non-living environment would actually produce, say, a combination like that. And there's clues that are even more obvious than these. And so, I love reading those science fiction novels from the 50s. I'm sure there's people here who do the same, where, the way we encounter alien life is we build a space rocket and then we fly, and in the not so sophisticated books, we fly at greater than the speed of light to get there quickly. And in the more sophisticated books, we have multi-generation ships, where people take 100 years to actually, get there. And then we find, alien life on the planet. And sometimes it's good and sometimes it's evil, whatever the author prefers. But actually, I think the real way we're going to discover high probability of alien life on an exoplanet is to just sit back in our armchair and look at telescope data over the next 10 or 20 years. So I think that's going to be one of the very interesting things. Artificial life is another one that people are thinking about a lot. And again, we have people right here on campus that are thinking of this. And both in a physical form and in computational form. And people are actually doing, let me talk about the experiments first and then the theory a little bit. People are actually doing both what I would call bottom-up and top-down experiments on this. So the bottom-up experiments are basically, if I want to make life, I'm going to synthesize a membrane, and then I'm going to synthesize some kind of information carrier, something like DNA, and put it inside a sphere of that membrane. That's like my protocell. And then I could synthesize some enzyme-like molecules that allow energy to be produced inside the cell that could drive duplicating that material and splitting that cell in two. And so there are people actually doing that. Nobody has succeeded yet. We don't have a real artificial life form yet where you can have something enclosed that actually has information, and then this information is used to snap it into two pieces and make two of those that can then continue to replicate. But people have actually made quite a bit of progress on some of the aspects, right? And so this is kind of the reductionist, can we synthesize life from scratch approach? And it remains to be seen how quickly people are going to be successful with that. And then there is the top-down approach that people also use, where what they've actually done is they've taken bacteria, which typically contain in their DNA thousands of genes to actually regulate all the proteins, how the membrane, how everything is made in that organism, allowing it to reproduce and all of that. And they have simplified them. So they're trying to work their way downwards to how simple can I make a bacterium and it still lives and is still able to divide. And the current record for a minimal cell is actually that it's gone down from several thousand genes to only about 400 genes. And of those 400, there's only about 50 left where we don't even know what they do exactly yet. So we know kind of almost 90% of what every one of those genes exactly does. And these simplified organisms are able to reproduce. In fact, people have shown that you can take one of these organisms and artificially synthesize its DNA on a machine, okay, then remove the original DNA from the organism, put the machine synthesized DNA in it, and the organism happily continues to live and will divide again. Right? So again, that's not like creating a life form from scratch yet, but it's working from the top down. And we'll see where people eventually meet in the middle on this. On the computational side, people are also trying to do computational work on a computer to bring life to life on the computer. And again, we're still fairly far away from it, but there's a lot of interesting work going on, where what people basically do is they take models of a cell, like this bacterium that you can see over there, and we have people working in this right here on campus, like my colleague and Jan's colleague, Zan Scholten. And they will have models that are kind of like a video game that has all of the pieces like ribosomes and mitochondria and all these pieces in there moving around like a 3D video game. It has thousands of chemical reactions, all the reactions that happen to produce energy or communicate with the membrane or do all of these things. And they actually have gotten it to the point where they can run these simulations for pretty decent amounts of time, like 15 or 20 minutes of real biological time, to actually see how this organism sort of behaves on the computer. Again, the big goal there is, which they have not achieved yet, is that they can actually build an organism with all the chemical reaction networks and running all of how everything diffuses and moves around, inside this bacterium in a computer, so that it will actually divide without you telling it, right? It's obviously you could write a code that says, and now let it divide or something like that. The key here is that you can just run this computer program. It doesn't have anything built in that says the cell will divide, but the cell will divide because it has the necessary ingredients to trigger that from happening. In physics and in science in general, we call these things emergent phenomena. It's something that you think at a lower level is built into the equations, like the chemistry and the physics of how this thing actually works, but it emerges out of those equations. You don't have, so all you have to do is you run F equals MA, right? And then the bacterium divides on the computer, and you didn't have to tell it that it has to do that. So that's the goal of these kinds of making artificial life forms in a computer. Another example is alternative fusion. And so fusion is one of those things, it's something so important and so good if we could get it to work, because it's a relatively clean energy source, that we have worked on it for whatever, seriously at least for 60 years or something like that. And of course, it's always 5 years away. I think in 1965, people thought it was going to happen in 1970, and in 2015, they thought it was going to happen in 2020, and it still hasn't happened yet. And there are sort of two main efforts in the world on how to do this. So in fusion, what you're trying to do is you're taking some lighter nuclei that are similar to hydrogen, and you squeeze them together, so much that they actually, basically, the nuclear surfaces touch, and then the nuclei fuse and make a bigger nucleus. And it turns out the bigger nucleus is lower in energy, and so there will be energy released, and then you can use that energy to do stuff. Okay? People are trying to do this either by using lasers to shoot them down on the surface of a ball of these atoms to squeeze them together, or they're doing it in Europe. This is the US approach at Lawrence Livermore Lab, or they do it in Europe by basically heating these things to a temperature of tens of millions of degrees, and then hoping that in this, what we call a plasma, that these high energy, like hydrogen-like atoms, that they just smash into one another and are going to fuse and therefore release energy. And nobody has really had success with that yet. But there are actually alternative possibilities for thinking about how to do this. So to give you an example, there's been a lot of work going on in the 1980s, 1990s. It's sort of kind of wound down now, in looking at catalyzed fusion. And the idea is that if you want to fuse two nuclei together, why not make a molecule? So then they're already fairly close together, like 1 angstrom or 10 to the minus 10 meters, very small distance, but they're pretty close already. And then if you can somehow get them to vibrate so they squeeze even closer, maybe they will collide together and then fuse. And it turns out there is a thing that was proved by a guy called Oppenheimer, who actually ran the nuclear project in the US in the 1930s, 40s, and 50s. He was put on the blacklist during the McCarthy era, the poor guy, but not through any real fault of his own. He actually proved that if you have a molecule, then the distance, the bond distance, how far the atoms are apart in the molecule, is actually inversely proportional to the mass of the particle that's holding the molecule together. So normally molecules are held together by electrons. So you have a cloud of electrons that sort of swirls around the molecule. Quantum mechanics describes how that works. And that gives you a certain bond distance of 1 angstrom. Well, it turns out there's another elementary particle called a muon, which is like an electron. It has still a charge of -1, but its mass is 208 times the mass of an electron. And so the bond distance is 208 times shorter than the bond distance you would get from a normal electronic hydrogen atom. So what they do is they generate muons in a particle accelerator, shoot them at hydrogen molecules. The muon knocks out the electron and inserts itself. The bond distance shrinks. And it turns out now the nuclei are actually close enough to one another that they fuse spontaneously. Okay? And then the muon is ejected and goes and does it to another molecule. And so it actually catalytically acts a bunch of times. However, here's the problem. We already would have fusion. Why don't we have fusion already, right, if this works so well? So here's the reason. In chemistry, we have something that we call the turnover of a catalyst, which actually tells us how many times in a row does it work before the catalyst goes bad. and doesn't work anymore, right? I mean, again, entropy messes up things in the end. So in chemical catalysts, usually what happens is the catalytic molecule falls into pieces and it stops working. But in this case, muons are actually not stable elementary particles, so it will just fall apart, and even with relativistic stretching, because it's moving pretty fast, it'll take about 10 microseconds or something like that, so a very short amount of time. So actually, what happens is the muon catalyzes this a few times, right? But then it's gone, and then you have to insert another one if you want to continue doing this. And it turns out, unfortunately, the energy you need in your particle accelerator to make that muon is more effort than you get back. Now, if the reaction lasted 3 times as long, if the lifetime had been 30 microseconds instead of 10 microseconds, right, then we'd be there. And people have tried, but no ado, right? There's nothing you can do. But what people have actually shown is that instead of doing this with muons, you could actually insert photons into the molecule and knock out the electron and actually use purely an electric field, which is basically what photons are, to hold the molecule together and to squeeze the atoms together. And it's been shown that you can actually enhance fusion in that way. There's in fact even a startup company that's trying to do it that way. Now, we're still far away from seeing if this could possibly ever work, but if something like this worked, it doesn't require any high temperature. It doesn't actually require any radioactive nuclei. It doesn't produce anything radioactive like neutrons, like some of the fusion reactions do. It produces only charged particles, namely what we call alpha particles, which are ions of helium, that you can run past the wire to induce a current on the wire to actually directly turn the motion of the particles into electricity. Whereas most reactors, whether they're conventional nuclear reactors or even the way people think about making fusion reactors, basically what you do is you make heat when the reaction occurs, and then you use the heat to heat up some steam. and then you have basically a steam engine running, right? I mean, this is still what reactors do. They're basically just glorified steam engines, even in the 21st century. So this would completely alleviate that, because these charged helium ions can just fly past wires, induce a current, and directly make electricity without that steam happening in between. So this is, I think, something very interesting that doesn't get like a huge amount of press. Another thing is consciousness, one of those big topics. Well, this is an interesting one. So I was just at a brain conference a couple of weeks ago, and so there were all kinds of people there, people more like biophysicists like I am, that are more like, I want to just know what molecules there are in neurons or something like that, to philosophers that think about, like, what is it even that you could scientifically research, and what things are we not ready to look at yet because there's just not enough information or experiments to do the right kind of experiments. And there was a lot of debate about, how you would actually define, when something is conscious or not, because, we all think we are ourselves conscious, but, how do I know? You are, right? I mean, in a sense, we all, on the outside, we just might be automated and just talking and moving and doing stuff, right? So, there seemed to be agreement, though, at this meeting on the kinds of experiments to do, and the idea that I sort of heard, that they are not being an expert in this field, by the way, by any means, is that, you have organisms that have sensory organs, and so there's, information coming from your senses, things you hear, things you see, and those are processed by circuitry, but that process alone is certainly not enough to have anything like consciousness happen, right? And then some of these things are actually stored. So like I'm seeing you sitting there or seeing you sitting there, right? And this is stored in my memory. I can close my eyes and I can actually see you in my mind's eye, where you're sitting, and imagine that you're still there. So there's this memory storage. And then one of the ingredients, at least, that people seem to agree at this meeting in consciousness is the idea that what has to then happen is there has to be a feedback loop in the brain, and there's actually circuitry in the thalamus and the cortex that are good candidates for this, that what it can do is it can receive external information, and then it can shut off the external information, but continue to receive a facsimile of it, because I have stored this in memory. In other words, I can imagine that you're sitting there, and by doing that, that's one of the ingredients in consciousness, that you know that you're not just receiving sensory information, but even when you no longer receive that sensory information, you can simulate that same information that tells you, there must be something there, because I don't need the outside world, right, in order to do that processing. So anyway, that was one of the interesting sort of ideas that came across at that meeting. Mind you, nobody there claimed that if we could show that that happens, that proves consciousness, but people thought that's at least an ingredient that you need, this ability to self-monitor, and then realize that, hey, even if I don't get its input from the senses, I must still be there, because I can actually imagine the input from those senses based on memory I have of those sensory inputs. Another thing, the last one that I'll mention, is tunneling chemistry. And this is actually like on the very physics, end of chemistry. So getting back to the theme again of entropy and generating a lot of waste heat or disorder, the way people usually run chemical reactions is you have a energy well. You can see two of those wells there, okay? And that contain, your molecule is in this energy well, the one that you don't want, and you want to make, let's say, the molecule over there. And it might be lower in energy or it might be higher in energy, like I drew in the picture, okay? So then what you do is you put heat in your system, and you heat it up high enough so it goes over this barrier. You can see there's a barrier between the two wells. And this is actually the only reason any chemicals are stable, right? Like, for instance, I am unstable in air, right? The oxygen around me, if there were no energy barriers, every one of my skin molecules would instantaneously combust and form CO2 and H2O and some ammonia, and maybe nitric oxide. And then everything would combust all the way down if there were no barriers, right? So the only reason we even stand here and I can talk about this is because there's energy barriers that prevent the molecules in our skin and our bones and our bodies from going to a higher entropy state, a more disordered state that consists of CO2 and H2O molecules. And say in a combustion engine, to go back to that example from the beginning of the lecture, you're taking these molecules that are hydrocarbons that are unstable in the presence of oxygen, and you're putting enough heat in with a spark from your spark plug in the cylinder to actually start combusting these molecules to turn into water and carbon dioxide. And then that generates enough heat to drive the rest of the reaction. So you have one stroke of the cylinder, you've burned up the stuff, and you're pushing the car along. Okay? So this is how we do chemistry. Like my colleagues in the lab, they just have flasks and they have heating mantles on them. They just turn buttons and heat them up, and then they hope they can collect the stuff that they want because you go over that barrier and then some of it comes down on the other side. But there is potentially a different way of doing chemistry that doesn't produce as much waste heat and therefore keeps sort of the entropy production down. And I illustrate that with the dotted blue curve, so not the bottom green one, but the next one up, and the purple curve that's almost lined up with it. So these things are actually what we call wave functions of the molecule. They tell us actually where is our reactant and where is our product. And so you can see the dotted blue curve in the middle there has like wiggles on the energy well that's on the left-hand side, but it's zero on the other side. So this would be a molecule that's the reactant molecule. Okay? And then the purple curve is zero on that side, but it has a hump on the right-hand side, and that corresponds to the wave function of a molecule that is on the product side, right? And so it turns out, actually, if we want to go from that reactant to the product, rather than putting in the heat, going over and then going back down, what you could actually do is if you can somehow, through an electric field or some other trick, just tune that purple energy level so it lies exactly on top of the dashed one. So you can see those curves are slightly offset from one another. Then actually becomes possible for the molecule to tunnel straight from the left-hand side to the right-hand side. This is one of those weird phenomena in quantum mechanics where you shouldn't be able to do that, right? Because it's kind of like, if I want to go to the basement of this building, I have to go up those stairs, and then I have to go over, and then I go down some other stairs. But I could also just go right through there because there's actually basement under you. I mean, obviously they're not wasting the space on solid, right? So there's stuff underneath here. And so it's as though I could do that by just walking to the chairs and disappearing and showing up on the other side without ever doing that whole thing of going up the stairs and going back down. Because again, going up the stairs wastes, produces entropy. So this is something that people are actually seriously thinking about. Can you actually drive chemical reactions by making use of quantum mechanics and by allowing directly wave functions to sort of jump over from one side to the other side to actually make the molecule that you want? And it might still require some energy to do it because you have to go from the very bottom dotted curve to that purple curve in the first place to even be able to go over to the other side at all, but much less because you have to go all the way up and then back down. So you're saving on the energy that's becoming non-productive energy, but that increases the entropy. So let's see. Yeah, I've got about. Let's see, we start 10:15, so I've got about 5 minutes left. Yeah. So let me actually. So I as usual, I'm not going to make it through the 8 slides, but that's okay. They're all independent of one another, so that's the great thing. I can just stop talking anytime I want. Well, maybe actually I won't play this one because I forgot to ask to hook the computer up to audio. So if you don't have the audio, then you're not going to see much. But actually, maybe I'll just mention very briefly. So this is actually a very abstract-looking thing which, however, is connected to my research. And I'll tell you how it's actually connected to my research. It's okay, we'll just do the video, it's fine. So what you're actually looking at there, this little red dot that's sort of moving in that blue cloud, and then once in a while, it's going to jump over again and come to the other side to this sort of random-looking web of trajectory. They try to go over, and this time, it's making it over. That is actually a protein folding, okay, in a very abstract representation. And it turns out that's one of the things that I study. And a few years ago, I hit it up with some musicians in our music department. Steve Taylor, who's actually interested in sort of sonifying scientific information into music, and Carla Scaletti, who works at a small company in town that makes sounds. You can actually make a living making sounds. How? Well, for instance, she made the voice of Wall-E in that Pixar movie, right? And so that's actually a pretty good income right there doing that. So they make sounds that then get used in movies or for other purposes. I started talking to her. I mean, she's really a great artist. And we actually came up with this idea that we can basically use these kinds of graphs where actually it turns out what you're seeing on the right-hand side there is the chaotic unfolded state of a protein, where the protein kind of just jumbles around like a chain in solution. And the blue thing on that side is actually when the protein is folded and is much more sort of rigid and in a well-defined structure. And the thing that we actually figured out is that there are certain things that have to do with that process that it's actually easier to listen to than to watch. Humans are usually very visual animals, and computer visualization is a very sophisticated business that has been sort of making progress for many decades. But people do much less sonification, which is the analog of visualization. But it turns out there are actually things that are easier to listen to. And one example of this would be that proteins, when they fold, are actually surrounded by large numbers of water molecules. And these water molecules actually account for about half the energy of that folding process. So it's not a negligible amount. You might actually say the water is folding as much as the protein is while that reaction happens. But it's distributed over 1,000 water molecules, and so it's very difficult to watch a movie that has 1,000 of those little dots moving around and seeing any kind of sense in it. But it turns out you can actually sonify the motions of the water, and then you can actually hear patterns. And it turns out that listening to these patterns actually allowed us to identify, for instance, which water molecules in what positions play a critical role in allowing the protein, again, to go over that barrier in the fold. What you were seeing there is, as it was going back and forth, and it's sort of like in the middle, going slowly, that was actually the protein going over the barrier, over to the other side in the chemical reaction to make the folded protein or make the unfolded protein as it went back and forth. So at this point, I have 2 minutes left. And so I'm just going to stop with the slide here and say a couple of things about it, and then happy to answer questions about what we've talked about so far. And this is one of those more, the sociology of science. And again, as a caveat, there are definitely people here on campus that are actually philosophers of science and historians of science and sociologists who study scientists that are much more, that they do this for a living, right? But there's nothing wrong. As scientists, we should think about these things as well, because we are practicing it, and it impacts our fields and how things work. And so specialization in science. A couple of hundred years ago, there was actually sufficiently little scientific knowledge that you could be a natural philosopher. You could kind of know a bit about everything, right? They are what we call Renaissance people, things of that sort, right? And that was really true. You could actually know almost everything about almost everything. But then, by the time we got to the 19th century already, we saw splitting into disciplines like chemistry and geology because there was just more detailed knowledge. However, at that point in time, you could still just get a bachelor's degree and then do 0 years of PhD and become a world-famous scientist. Like Charles Darwin never got a PhD, right? And I would say, arguably, Charles Darwin is a world-famous scientist. And then by the beginning of the 20th century, even chemistry, I'm just picking an example, I could pick other disciplines, sort of became specialized, that we have organic chemists that make things and physical chemists that break things. At that point, you did have to get a PhD. By the 1960s, even physical chemistry was getting too big, and so you had people that were, let's say, nuclear magnetic resonance spectroscopists or electronic structure theorists or things of that sort. And by that point, by the way, in the 1960s, you basically took about 3.5 years to get your PhD and 0 years of postdoc. So like my advisor in the early 1980s at Berkeley, he wrote 3 papers as a graduate student, did not do a postdoc, and got a full professor job at Berkeley. I think now any graduate student sitting here, they're going to laugh, right? No way is that going to happen in the year 2022. Then things became even more specialized. The nuclear magnetic resonance spectroscopy become solid-state bio-NMR experts or hydrogen exchange experts and so forth by the 1980s. And we've gotten up to the point now where it actually takes typically 5.5 years to get a PhD. And if you are interested in getting an academic faculty job, it takes 3 years to do a postdoc typically after that, to even get to the point where they'll let you, into university as a professor. And of course, knowledge has become so complex and so, there's so much of it, that actually the NSF even almost has stopped funding individual scientists. I mean, they still do, but I'll be completely honest with you, I actually am no longer writing individual investigator NSF grants. And the reason is they haven't changed the amount of money for the last 30 years of one of these grants. And so 30 years ago, I could actually run a research group on one of these grants. And now it basically pays for the lunch. And that's it, right? So it's actually not worth the time that you spend, putting the pen on the paper to actually write a grant. But instead what they do, which is certainly also very nice, is they fund collaborative centers like one that Jan and I were in, where you have multiple scientists with different specializations actually working together. So we've gotten to the point where it's often not even a single scientist with one group doing things anymore. It has to be like a whole bunch of professors, with multiple groups that actually get things done. And again, we're now at pushing, I think soon it'll be 6 years on average. Actually, it is already in biology. In biology, a lot of people do 6 or 7 years of grad school and do 4 or 5 years of postdoc. And the result of this is that you have these brilliant young people, and they're like 37 years old when they become a professor. I became a professor at age 28, right? The guy that taught me from Berkeley about this, he was a professor at age 23 at Berkeley. And, I mean, whatever you want to say, I think you're better off actually giving, young people more time to their own stuff and start in their 20s rather than starting them in their late 30s, which is where we're headed. So this is a real problem in science. And honestly, I don't know what the best solutions to this are. But I have some ideas if, anybody wants to, ask in the questions of maybe what one might be able to do, but, who knows. Okay, so with that, I'm going to stop here because, it was supposed to be 45 minutes, and I'll be happy to take questions.
Thanks, Martin. Let's take,
and we'll do the other 4 slides some other day.
so let's take some questions from the audience. And Martin,
I'll
to repeat the question.
Exactly.
I have a question about the consciousness.
Mm-hmm.
So, do you think the single cell organisms like bacteria, do they have consciousness?
Okay, so I'll tell you. So the question is, do we actually, or do I think that single-celled organisms like bacteria have consciousness? Okay. And so let me give you my answer, but this is purely an amateur answer, right? Just so. But I'm willing to put my foot forward and give you my amateur answer. No, and the reason is that they do contain some feedback circuitry, but they don't have the kind of memory storage and memory recall that I think allows them to do this by this definition that I talked about, to actually do what I talked about there. Now, you could, of course, make that question harder for me, even, by sort of working your way up, like, what about a multi-celled organ, and eventually I will definitely answer yes, for sure, right? I have no doubt, for instance, that primates have consciousness essentially at the same level that we do. And I think you can go down quite a ways and still, answer that question with a yes. But of course, to some extent, the answer to a difficult question like this is going to depend on really what is your definition, functional definition. And the thing that I mentioned there is just a sort of functional minimum that a lot of scientists who work on this think has to be satisfied. But it's what they like to call a necessary, but not necessarily a sufficient condition. So, by the way, I mean, one of my favorite things that I threw out at that meeting, just to make people like, what the heck is he talking about, is I basically asked people something at the opposite end of the spectrum, but the same kind of idea, which is, do you think the 8 billion people on Earth are a conscious organism? Right? Because we are a network that talks to each other, transfers information. How do we know that this 8 billion thing is not actually very slowly thinking deep thoughts, and we're just cells within it that communicate and make things happen, and we just don't even know it, right? Because individual neurons in our brain certainly don't know that we think that we're conscious. Right? So but it's the same kind of idea, but at the opposite end of the spectrum. I'll let you pick the question.
What was the answer to that question, by the way? You posed that question to this group of scientists.
Oh, what is my answer?
No, what was their response to you?
Their response was, we don't know. Which is a fair response.
Let's take a question from you.
Yes, on your protein folding
Uh-huh.
you showed, could you just speak to the recent advances in protein folding modeling?
Yes. So let me talk a little bit about that. So it turns out actually, and I think you're probably thinking of AlphaFold and these kinds of things, right? So there's actually two problems related to protein folding that people have been investigating for, the last 50 or 60 years as well, just like nuclear fusion, although we have got more answers. One is actually the actual mechanism, the dynamics by which a protein folds. Like what is actually happening when a protein folds? What are the steps that allow it to fold? What do the water molecules do and other kinds of things? The second question is just, I don't care about any of that. I just want to know, tell me what the structure of the protein is. I don't care how you get the answer. Okay? And actually both have made a lot of progress. So we understand much better now what it is actually that contributes to protein folding, how water molecules, entropy changes and so forth are involved in making that happen. But people have also made a lot of progress in just tell me what it looks like. What does the folded protein look like? So a program like AlphaFold actually is based on software that has been going back 30 years at least. In fact, before AlphaFold came out about 2 years ago, people had gotten from these kinds of computer programs a predictivity of about 70%. Not super great, but not really bad either. And then it took a company, like Google, to actually invest enough, large amounts of cash, way more than we scientists get in our grants, to actually push that from 70 to 90%. And what that software basically does is it uses actually tens of thousands of experimentally measured data points of proteins where people have measured the structure by doing X-ray crystallography or other methods to actually figure out exactly atom by atom what the structure of a protein looks like, and then feeding that into a neural network to then allow that to predict other structures that are not in that database. But the time was ripe for that only now. So the reason that AlphaFold didn't come out 20 years ago is you actually need a large amount of data to train this kind of AI or machine learning software to do this job. And so the time was really only ripe for that a few years ago. But the way I look at it as an insider in the field, AlphaFold is not some kind of, wow, all of a sudden we went from 0 to 100 in one step. AlphaFold is an incremental improvement on something that was 70%, and 10 years ago it was 60%. And at some point in the early 90s, it was like, there were no predictions. You really couldn't predict anything at all. But 90% still is impressive, and the reason is it's the kind of confidence that actually now people could do things like if you want to design a drug, and you have a protein that's not quite like anything in the database, you will predict it using that software. And you can be pretty sure that the structure is accurate enough that you could, for instance, do a drug docking study or something like that on a computer and actually get a reasonable answer from it. So this is where there is a big difference, in a sense, between 70% and 90%, even though this whole thing sort of builds on older things.
Is it equally done in the environment the protein is in, and not just the chemical makeup?
Yes. So he's asking, does this also depend on the environment, the proteins and not the chemical makeup? So actually, the answer is Jan and I, for instance, studied this question. And it turns out if you take let's say, an organism like a fish, okay, and it has many different tissues, muscle tissue, nerve cells, skin cells, and so forth down the line. If you actually, and we can do experiments where we can actually look at just one single type of protein inside a single cell inside a fish. We in fact even have apparatus on campus where you can look at a single protein molecule in a single cell that has billions of molecules in it in a whole animal, right? And actually follow that one single protein with nanometer resolution, how it's moving around in that organism. And basically what we find when we do these experiments is that even the same protein in different cells in different tissues of an animal behaves differently already. So the environment really does make a difference in what a protein can do, how it folds, and how it behaves. Okay,
Questions? I think I saw someone raise their hand.
I think you maybe. Yeah,
yes.
there we go.
Yeah, mine is more of a quality type question. Can you characterize the major donors to scientific research and also the recipients? And what would be the reason driving those donors to give money?
So, There's the slide on it. I didn't get to it. But let me end, don't worry, I will answer your question. So I'll repeat the question. Who are some of the major donors involved in allowing science to progress? And what can one say about demo recipients? What is like, maybe making them special or different? Is that kind of, the gist of it? Okay, so, science funding has actually changed a lot from the old days when basically people had to be wealthy and funded themselves, like Darwin and his family, right? To, in the 1940s and 50s until the 80s, government foundations like the National Science Foundation. And I think now we're actually kind of going back again to more private donor funding and more private organizations that are stepping in to rescue the day. And some of these organizations specialize, and I think those are the most valuable ones, on young scientists. Again, that problem of how do we really help young scientists. So there are places like the Packard Foundation or the Beckman Foundation. Beckman also built this nice building on campus that are actually investing tens of millions of dollars or even hundreds of millions of dollars in actually providing funding for young scientists, people who are hopefully as young as possible and are assistant professors, even postdocs, trying to do it at a young age, and giving them large enough amounts of money that you can really do something with it. Because if you give somebody nowadays a $50,000 prize, well, you can barely even buy like one balance for that in your chemistry lab, right? I'm not kidding. And so, it takes more than that, and these foundations actually provide more. But then also actually private donors too. So I'll mention the example here. You see this thing that says Anton at the bottom. So it turns out, on a computational basis, maybe also going back to your question, a large fraction of the solution of not predicting the structure of a protein, but how a protein actually folds, what happens during the process, was actually pushed forward by a single person, David Shaw, not by the National Science Foundation or any of these places. And what happened in his case is he was a computer science PhD. He got out of computer science and into the stock market in New York. He built up a company that did derivatives trading and became a billionaire. And then when he was about 50, he decided, enough of this, I have enough money, and I'm going to invest it in science. And so he got a team of about 100 biophysicists and computer scientists together. And they built the world's fastest supercomputer, which at the time, about 12 years ago, was about 100 times faster than the next fastest computer for doing calculations on proteins. And the reason was that unlike IBM, which built this computer Blue Gene, he didn't have this need for his computer to also then be able to be saleable later on. So IBM was hampered by the need that they wanted to make a supercomputer and they wanted to do proteins on it. But when they were done, it was just a toy. They needed to be able to sell it to banks or whoever as a supercomputer. So he said, forget about that. I'm just going to build a computer that can only fold proteins. It doesn't do anything else well, but it'll do this thing really, really much better. And so this really helped. And what he did, in addition to doing these calculations himself, he actually donated free supercomputers. I mean, these are like tens of millions of dollar instruments a piece, right? And he donated them to supercomputing centers in the US, like the Pittsburgh supercomputing centers, that provide computation time free of charge to scientists. So like I run on these computers, right? And I don't have to pay anything at all, actually, to run on it, other than to write a little mini grant. And so again, there's the impact of like one person, right, acting as a donor, in this case of hardware, right, that has really helped push science forward.
So that sort of lowered the entropy?
Yeah, you could actually say so, exactly. Well, if I, I don't want to sound too cynical. I don't think there's anybody from the NSF here, but writing grants, it generates a lot of entropy, and so if I don't have to do that, then yes, it's definitely lowering the entropy of the process.
Let's take a question.
What's your opinion of the disseminated generation of ideas from citizen science projects and follow through that?
Yeah, so actually, I think these are really important projects in the long term. And just like, you remember those days when the Wikipedia was a joke, right? And I certainly remember them as well. And there was a lot of misinformation on it. And people were actually very skeptical. Could this ever replace like a real encyclopedia? Right? But it turns out, actually what ended up happening is the Wikipedia actually did get better with time and actually is fairly reliable. There are certainly subjects that are less reliable than others, but I would say in the scientific and engineering subjects in general that maybe are a little less politically controversial, things of that sort, it actually does very well at having reasonable information in it. And so I think it's the same thing with citizen science projects. So, for instance, the field of astronomy, I think, is in general way ahead of chemistry and physics with that all the observational data from large space telescopes, from the Keck in Hawaii, all of this, it's all available online to you. You could actually go there and analyze data if you wanted to publish papers. In fact, I'm not a astrophysicist or astronomer, but I am an amateur astronomer, so I really do like the subject. And one of my bucket goals is that I will analyze some of this data and write a paper and send it to the Astrophysical Journal and see if I can get it published, right? We'll see. But I think this is actually great, and because it allows access to people that are just interested in doing science. They may not have all the formal training. And it turns out that actually some of these teams of people, of amateurs who have trained themselves and have become really pretty expert, like Darwin was basically an amateur who trained himself, right, to do the stuff that he did. They have actually published papers that have good scientific content that talk about things like relationships between variable star, sort of on and off times in other galaxies, and how you can sort of correlate that with rotation and mass of galaxies. So there's all kinds of interesting stuff that has already come out of this. And I think there will be simply more of that as this develops. And there is data like that available in, going back to AlphaFold again, right? The company, Google, right? You might say, well, what a breakthrough, right? They had these brilliant computers and whatever, and then they came up with this predictor that works 90% of the time. But you have to realize the only reason they could do that is because there was a database that was set up at the cost of 60 years of research by the NSF and other places, where thousands of scientists like me and other people in physics and chemistry, whatever, measured proteins and made that database, and they just got it for free. And there's definitely $100 million worth of work in that Google just got for free. Right? And anybody can go in there. So there's lots of protein problems that are still unsolved. And the data is there in this database, and you can just go to it and play around with it yourself if you're interested. Yeah, it's all accessible. There's this game called Folding at Home, right? For instance, that you can play, where and there's a related video game where you can actually just play around, juggling the protein to actually fold as a computer game. And it turns out actually people do pretty good at folding proteins in this computer game if you give them a reward for coming closer to the correct structure. So.
More questions?
I can do one more.
Okay, go ahead.
If you don't mind.
Nope.
Without actually playing the song, can you describe what Inside Plug In that you did get from the song?
Okay, so let me talk about the song one more time without too bad, because Carla's a great artist, so it really sounds good. But next time I'll remember to plug it in. So basically, the insight that we got from this song is that we were able to hear by sonifying when certain amino acid residues in the protein make a contact with water molecules and then break those contacts, which combination of these contacts that are being made and broken are actually important and occur in what we call the transition state, when the protein goes over from the unfolded side over to the folded side. And this was essentially impossible to tell by visualization because there's so many possible candidate water molecules. But with the sonification, the important ones, by tweaking the sound correctly, were sticking out. Then we could actually go back afterwards and find which ones they were, and then visualize them and find, it's this guy in there out of those 1,000, right? That's the one. So this is really where it helped us. So I think auditory processing can be very useful for any kind of thing that's sort of a complex time series, right? Where something that changes as a function of time, where multiple bodies, like 1,000 water molecules, contribute. And so it's very difficult by eye to see the trend, but if you turn it into a sound, you can actually hear the trend.
Here we go.
Ever since I took my first physics course in this classroom back in the 60s, it seemed to advance now to experimental techniques. I'm just curious when you think you'll ever go back to a theoretical advancement like, for example, the Einstein and Bohr.
Yeah. Well, so there are certainly advancements like this that are to be had. I mean, let's take the consciousness example. I think there's actually theory, systems biology kind of theory that could help inform that. And certainly we know that there are at least some small cracks in the standard model, right, based on the most recent experiments at the accelerators. And so it's of course impossible to predict when, right? Because the really big insights, like standard model or Darwinian theory of evolution or things like this, they're pretty far and few in between. And you wait for like 50 years and then it happens again. But for instance, I have an inkling that there is actually enough amiss with some of the accelerator data now, that we're not at the 5 sigma level, but we're moving towards it, that there will have to be something done that like the standard model, for instance, is not describing properly right now. Or in the field of biology, again, it turns out there are actually theorists who are thinking about what are actually the requirements for something to come to life. From a theoretical point of view, what is it that's the difference between something that's just a bunch of dead chemical reactions and something that's alive, and deriving a formalism for that? And again, you're right, that's also mostly an experimentally driven field, but there are theorists in this who are trying to actually come up with conceptual frameworks for this, and I already mentioned the consciousness example. So I think these are like 3 cases where there could be really big theoretical breakthroughs, and they will be necessary to give experimentalists the framework of how to think about these problems properly. But, who knows? It could be 5 years, it could be 20 years. It's hard to say. Say again? Yes, I am. But as people can probably tell from listening to me, I'm pretty much an inveterate optimist. So you're going to always get a yes, I think we can do this, answer from me. Yes. Okay, so that's a good question. So she's asking, if you want to do chemistry by tunneling, is there kind of a limit to how many molecules can you process by that mechanism to go from one side to the other? And the answer, no, not necessarily really, because the way you could imagine, for instance, this experiment working is that you could make a beam of molecules that's cooled down to ultra low temperature, and then you might intersect them with a laser beam, and this laser beam does that excitation, and the electric field gets the tunneling going. And then you could just send a stream of molecules into this, and then you would get the other molecule coming out at the other end. In fact, people have actually done experiments like this, where we transform one molecule into another through tunneling. But these are very expensive experiments that still don't have very high throughput and require gigantic vacuum, liquid helium apparatus, all those kind of things. So it's not an industrially practical thing. It's only kind of a proof of principle. But there's nothing in the laws of physics that says that we can't, make this less expensive and simplify it down to the thing where it might be commercially viable. And, again, the inveterate optimist speaking here, I'm like a big fan of the Star Trek television series from the 60s, which was kind of an optimistic, like, we can be friendly with one another in outer space and thing. And they have this machinery where you say coffee and then it goes, and a coffee just appears, right? And you could actually imagine that tunneling chemistry would do that. It would take atoms, assemble them through tunneling, and you could just make objects appear. So there's nothing in the laws of physics that says it's not possible. Now, when you're doing that, you're certainly reducing the entropy of these atoms by a lot. So there has to be, of course, some mechanism that provides the necessary neg entropy for that to happen. But there's nothing that says in the laws of physics that you couldn't actually build something like that. Again, how long is that going to take? Well, probably even longer than some of the theoretical progress that we were just talking about. But hey, Star Trek plays in the year 2300 or something like that, so we have time.
Oh, yes.
The future of training of becoming a scientist. Yeah. So, this is one of the things where some of the stuff may actually, Back to the Future may be the best thing to do. So I'll give you one example. And I don't know if this is true in physics, but it may be true there as well. It certainly was true in chemistry. In the 1970s to early 1980s, the whole scheme of how students in chemistry were trained was quite different from the way it is now. What actually happened at that time is that places like the National Science Foundation would give grants to departments, not to individuals, for funding students. And so a student could actually get a research assistantship that was a fellowship that came directly from the NSF, and that was handed out by the department. And then, around that time in the early 80s, what began to happen is that individual investigator grants grew in size. And at that point, professors started paying the students. So it's like, you join my group and I'm going to pay your salary. And then this has sort of continued to evolve to where there's a lot of pressure that you need to get certain things on the grant done. And you can't just kind of kick back and say, hey, let's just try anything that's interesting. And the price is that students have become inordinately dependent on professors. That used not to be the case, at least in chemistry, like 30 or 40 years ago. And like if I were to change something, right, at the NSF, maybe I'll try and become the NSF director someday or something, if I feel strongly enough about it, which I feel pretty strongly about this, is we actually need to look at some of these things and maybe say, I think the best thing that you can do as far as empowering postdocs and graduate students is to put the money in their hands, at least the money for their own salary. Maybe not the money for all the lab equipment and stuff, because you need to have continuity and you want a research advisor and all of that, right? I mean, as I said, apprenticeship, right? That's one of the important things. But basically, give students the power so they can just say, like, I tried this and that didn't work, so I'll go to another lab and I don't need to go through any hoops and rigmaroles because I'm already paid. And so I can go to somebody else and say, hey, I want to try that instead. Are you okay with that? Also, I think this would also empower people to graduate earlier because you're not completely in the hands of a professor. So, I mean, I'll give you an example, which is kind of a joke, but I wasn't laughing when it happened. I was working at Berkeley as a grad student, and I was working away, and at some point, 4 years in or so, I had published 15 papers, and so I went to my research advisor, and I asked him, like, could I maybe graduate at some point? And he said, like, yeah, if you had asked me half a year ago, I would have let you graduate. I'm like, oh, yeah, I should have asked earlier, right? And he was a very nice advisor, so it worked out really well. In fact, I learned a lot from him, I think, on what's a good way to try and run a group. But I would say you need to give even young people a significant level of independence. It's still an apprentice process. You need labs, you need research advisors, but it should become more again of an advisor and an apprentice relationship, and the apprentice is kind of independent, right? As opposed to a professor and a laborer who works for that professor, which is not a very good way to do science, in my opinion. So.
One last question. Is that okay, Martin?
Yeah, one back there or over there. Yeah.
We'll get you next.
We'll do both.
You go first.
Almost all, or maybe all the papers that get published about things that work. Wouldn't it be useful to publish papers about things that try and don't work?
Do I ever wish? It has gotten a little better over the last 10 years, I think. And part of the reason is that the culture in science has gone from really just describing in a very brief paper, like what worked, to actually having supplementary information and stuff like that that can be quite voluminous. And there are actually research fields, maybe not so much in physics actually, because I read a lot of physics and biology papers, but in biology people have actually gotten used to the idea of putting in the SI, like this didn't work and that didn't work. And so many times have I wished, I had that in a paper where I thought, I read this looks great, let's do something with that, and then I'm doing it and it doesn't work. And sometimes it's because they left out some detail of something that didn't work that they don't even mention. Don't do that, do it in this slightly different way. And sometimes, of course, it also just turns out there's something wrong and it just plain isn't going to work. But that's how it is in science, right? Not every paper is going to be right. So it would actually be really nice. And there are journals and things like bioRxiv and open access journals that actually encourage that and encourage at least putting some of the things that didn't work in there as well. And I don't think it has made it as deeply into physics yet, as far as I can tell from reading like PhysRev journals or PhysRev letters or PRX or things like that. But I would say in biology, it's already well on its way. And so I think this is going to spread more. Because why not, right? I mean, one reason in the old days, if you want to be charitable, right, that we didn't do it is because print space is precious and you have journals on shelves. Well, now it's all on a computer screen. I just push a button and bring up as many pages as I want. In fact, journals have changed because of that. So like PNAS, which is a journal of the National Academy, used to have a strict 6-page limit on papers because you had to print the stuff. But now they do allow up to 10 pages if you really want to, although they still say, please make it 6 if you can. And most people are not abusing it. But yes, this is really important and we need more of it. And I think she had a question over there.
So you mentioned how your advisor was able to become a professor at Berkeley at such a young age. And so, how has that changed your perspective of learning from someone who's taken a lot less schooling, of just this different perspective and respect for your colleagues and peers who now have to go through so much different schooling, and how has that kind of changed and impacted how you
Right.
engage
Right, exactly. So, you know, in science as everywhere else, respect, of course, comes really from what have you learned, how do you know how to manage people, how do you know to do all those things that are necessary to run a research group and make scientific progress. And, you know, some people might be better at it at age 23 than others at age 60, right? I mean, you know, who knows? And I mean, my advisor had all my respect because he was just a good scientist and also knew how to manage people pretty well, which is not something, it's something one has to learn as well. And scientists often get no training in it whatsoever, really, other than by observing as a graduate student or a postdoc what your advisor is doing. So I think there is a real trade-off, like what you're saying, in the sense that if you get more training, especially because we have more specialized knowledge, so you need somewhat more training, right? So that helps. But on the other hand, if you wait until somebody is, you know, really, really getting on in age, you're giving them a much shorter career and less opportunity to actually make discoveries, right? Like one of my colleagues jokes that, you know, as a mathematician, you're over the hill at age 18, right? I mean, that's probably an exaggeration, but still, I think you get the picture. And so we need to find a balance in that. And the balance has really shifted by like 4 years total since the 1960s. And my suspicion is that we're way too far in the long side at this point. And you know, you could argue maybe in the 1960s they went a little too quick, but we're getting to the point, you know, what are we going to wait for? Until people are 50 and they're assistant professors? You know, at some point, right, we need to put an end to this.
Great. I think that's a good place to stop. It's 11:30. Let's thank Martin again for a lively discussion.